Structural analysis and topology optimization of leaf spring bracket. Abstract leaf spring is a basic form of suspension, widely used in commercial vehicles like tempo, truck etc. It is made up of layers of long steel plates of varying lengths, sandwiched one upon the other. Leaf spring is attached to chassis with the help of leaf spring mounting bracket. Shape and size of the bracket differs from vehicle to vehicle. As bracket acts as a link between chassis and suspension, it can be redesigned in optimum manner, such that it will have low weight and can efficiently transfer stresses without failure. In this paper, we have done weight optimization of leaf spring bracket of LCV diesel truck, using topology optimization method. Leaf spring bracket is modeled using CREO 2.0 software. Real condition forces and constraints are applied on bracket. Static and fatigue analysis is done using Ansys software. Topology optimization of leaf spring bracket is done in Ansys 19. Final optimized bracket is redesigned as per result generated by topology optimization in Ansys and manufacturing feasibility. Static and fatigue analysis is carried out on an optimized bracket design. It is observed that stress value in original and optimized bracket remains same. Strain gauge testing is conducted on optimized bracket. Strain value measured on strain gauge at 6000 and load is 153.2 microstrain and strain value measured in FIA at same load and location of strain gauge is 180 microstrain. Weight of the bracket is reduced from 1.8 kg to 1.6 kg, i.e. 200 grams, which is equal to 12% of original bracket weight. Hence, weight optimization of leaf spring bracket is done using topology optimization method, without degrading the bracket performance with respect to original bracket design. Keywords: leaf spring bracket, strain gauge, topology optimization. Introduction. In recent years, automotive industries are emphasizing on increasing vehicle efficiency by optimizing part weight without compromising on part quality. Optimization is mainly divided into three types: shape optimization, size optimization, and topology optimization. Shape and size optimization is the traditional method of part optimization, followed in industries from many years. Topology optimization is upcoming way of optimization, which consist of mathematical method of optimizing material layout within a given design space, with predefined loads and constraints, with the objective of minimizing weight, volume, or maximizing performance. Topology optimization is done using FIA software. There are various algorithms used for topology optimization. Most of the optimization software use density-based approach, in which each element in the design space will have its own stress level and strain energy. Elements having higher stress level, 1, are retained and elements with zero stress level are eliminated unless overall structure is not affected. Topology optimization targets number of elements to get rid of, which depends on input values given by designer. In this paper, topology optimization method is used for weight optimization of leaf spring bracket. Leaf spring bracket is the connecting link between the leaf spring and chassis. It is non-movable part and hence has good scope of optimization. Leaf spring bracket of LCV diesel truck has been analyzed and optimized to reduce its weight without compromising the strength. 3D modeling of part is done in CREO 2.0 software. Analysis and topology optimization is done in Ansys 19 software. Problem statement is to optimize weight of leaf spring bracket using mathematical optimization technique, i.e. topology optimization using Ansys. Compare FIA results of original and optimized bracket. Perform experiment validation using strain gauge testing. Figure 1 gives the methodology used for topology optimization. 2. Analysis of leaf spring bracket. Leaf spring bracket specifications. 1. Vehicle: LCV diesel truck. 2. Material: SS4012AE345. Bracket material specifications are given in Table 1. See load and constraints. After studying original bracket assembly in vehicle, constraints and loads are applied in following manner. 1. 6000 N vertical load is applied on big holes, through which pin carrying one end of leaf spring passes. Vertical load is applied, as force is experienced in vertical direction when vehicle passes from pothole. 3 holes on vertical triangular plane and 2 holes on horizontal plane of bracket are bolted to chassis. Hence they are fixed. 3 Displacement of bracket in y direction is 0. Hence horizontal plane is given 0 displacement in y direction. D. Statistic analysis of original bracket. After applying constraints and forces on bracket, static analysis is done in Ansys. Total deformation, stress, and strain are measured on original bracket. Refer Figure 4, Figure 5, and Figure 6 for the total deformation, equivalent stress and equivalent strain. Total deformation in original bracket is 0.13 mm. Equivalent stress in original bracket is 67.9 MPa. Equivalent strain in original bracket is 536 micron strain. E. Fatigue analysis of bracket. 1. Theoretical calculation. 1. Ultimate stress of bracket equals SUT equals 400 MPa. 2. Endurance limit of bracket equals SE equals 170 MPa. 3. Equivalent stress on bracket equals S equals 68 MPa. Refer Figure 7 in which log S versus log N curve is plotted. Equivalent stress in bracket is less than endurance limit. Hence life of bracket is more than 1 million cycles. In below diagram it can be seen that at 68 MPa bracket can sustain up to 10 superscript 1 superscript 2 cycles. 2. Ansys results. Fatigue life of bracket is more than 1 million cycles, both theoretically as well as in FIA. Refer Figure 8, for fatigue life of bracket. Also it is observed that factor of safety for most of the bracket is 15, whereas in automobile factor of safety is maintained up to 2. Hence there is large scope of bracket optimization. Minimum factor of safety is 2.018. Refer Figure 9 for factor of safety. 3. Topology optimization. Optimization of leaf spring bracket is done using Topology Optimization module in Ansys Workbench 19. 1. Step 1. Define optimization region. Define design and non-design region. Non-design area is that part of the bracket which is attached to other assembly parts, whereas design area is that part of the bracket which is not in touch with any peripheral parts. Hence all bolted joints and loaded area is non-design region and remaining area of bracket is considered as design region. Figure 10 shows the design and non-design region defined for bracket under study. 2. Step 2. Define objective. Objective is to minimize the compliance. 3. Step 3. Give response constraint. We want to optimize 20% of bracket mass. Hence our response constraint is to retain 80% of mass. 4. Step 4. Solution. Topology optimization runs various iterations to reach to final solution. Below Figure 11 shows the topology optimized bracket result generated by Ansys. Fig.12 Topology optimization result from Ansys. After getting topology optimization result, 3D model of optimized bracket is created in CREO. Final bracket is designed considering manufacturing feasibility, hence does not match exactly with the topology optimization result. From the result obtained in topology optimization, horizontal plane of bracket have square shape cutout which can be manufactured, but vertical triangular plane cutout need to be redefined based on manufacturing feasibility. Hence we carried out shape optimization here, to select best shape from 3 basic shapes, i.e. triangle, rectangle, and circle. Below Figure 13, Figure 14, Figure 15 shows basic shape cut stresses generated due to cutout. Refer below Table 2, which gives comparison between basic shape cutouts made in vertical triangular portion of bracket. From Column 2, it can be observed that maximum equivalent stress value in all 3 geometries is equal and same as original bracket. Column 3 gives stress generated at local area due to cutouts and is not applicable for original bracket design, as it does not have any cutout. But for remaining 3 shapes, stress value is almost same and very less compared to yield stress of bracket. Column 4 in the table gives stress generated at corner of various shapes. It can be seen that circle shape cutout does not have corner stresses. Hence we selected circular shape. Thus, considering both topology optimized results and manufacturing feasibility, final optimized bracket is made in CAD model. Refer Figure 16 for final optimized bracket. Fig.16 CAD model of topology optimized bracket. For analysis of optimized bracket. A static analysis of optimized bracket. Force and constraints, similar to original bracket, are applied on optimized bracket. Static analysis is done in Ansys. Total deformation, stress, and strain are measured on optimized bracket. Refer Figure 17, Figure 18, and Figure 19 for the total deformation, equivalent stress and equivalent strain. Total deformation of original bracket is equals 0.125 mm. Maximum equivalent stress of original bracket is equals 66.7 MPa. Maximum equivalent strain of original bracket is equals 490 microstrain. B. Fatigue analysis of optimized hanger. Fatigue life of optimized bracket is more than 1 million cycles in FIA. Refer Figure 20, for fatigue life of bracket. Also it is observed that factor of safety for most part of the bracket is 15. Minimum factor of safety is 2.02. Refer Figure 21 for factor of safety. Hence optimized bracket is also robust. V. Manufacturing and experimental validation. A. Manufacturing. Optimized leaf spring bracket is manufactured using 3 machining operations which include wire cutting, vertical drilling and milling. Below Figure 22, Figure 23, and Figure 24 shows operations used for making of optimized bracket. Figure 25 shows the final optimized bracket. Leaf spring bracket of LCV diesel truck is made up of sheet metal, hence horizontal slot and hole can be made using punching operation in actual part. Further, for experimental validation boundary conditions need to apply. Hence fixture is manufactured using welding process as shown in Figure 26. B. Experimental validation. For experimental testing, strain gauge testing is done using UTM machine which is used to apply load of 6000 north on leaf spring bracket 1. Refer Figure 27 showing strain gauge testing setup. Strain gauge should be mounted at the location on bracket having maximum stress value. But in leaf spring bracket, maximum stress is obtained on bend. It is difficult to apply strain gauge on bend portion, as it may not adhere properly to the surface. Hence strain gauge is mounted on horizontal surface of the bracket, near to maximum stress location. Refer Figure 28 showing strain gauge location. Load is gradually increased from 0 to 6000 and strain value is recorded using data logger. Strain value obtained is converted into stress to get the respective stress value. Strain value obtained on strain gauge is 153.21 microstrain at 6000 and load, which is equal to 31.5 MPa stress, which is very less than yield stress of bracket. Refer Figure .29, which shows force vs strain graph obtained from strain gauge testing data. From graph we can see, as the load is increased gradually from 0 to 6000 n, strain value also increases. Strain value obtained at 6000 n is 157 microstrain, at which stress value is 31 MPa, which is within yield limit. To get the correlation between experimental and FIA results, experimental strain values are compared with FIA strain values at strain gauge mounting location, for load increasing from 0 to 6000 n. At 6000 n load, experimental strain value is 157 microstrain, i.e. 31.5 MPa, and FIA strain value is 180 microstrain, i.e. 36 MPa. Thus strain and stress values obtained experimentally and FIA are almost same and are within yield stress limit. Refer Figure 30 showing load versus strain graph experimental and FIA data. Thus, strain values obtained experimentally and in FIA at strain gauge location are same. Thus, experimental results are in line with FIA results. Hence, maximum stress value obtained will also be same as that of stress value obtained in FIA, which is 66.7 MPa. Hence, stress values of the optimized bracket are within the yield stress limit. 6 Results. Refer Table 3, showing comparative results of original and optimized leaf spring bracket. We observe that FIA results for original and optimized bracket are almost same and weight of part has reduced from 1.8 kg to 1.6 kg, which is equivalent to 200 grams. Hence we obtained 12% mass reduction. From below Table 4, we observe that experimental result match with the FIA results at strain gauge location. Hence, maximum stress value obtained experimentally is also same as FIA, i.e. 66.7 MPa, which is below yield stress value with FOS 5. Hence, optimized leaf spring bracket is robust. 7 Conclusion. 1. Topology optimization technique can be effectively used for part optimization. 2. By using topology optimization method, weight reduction of 200 grams i.e. 12% has been achieved, without increasing component stress. 3. Maximum equivalent stress in original bracket is 67.9 MPa and maximum equivalent stress in optimized bracket is 66.79 MPa. Hence stresses in the optimized bracket does not increase, thus life of bracket is not affected due to optimization. 4. Minimum factor of safety for original and optimized bracket is 2 and maximum factor of safety is 15. Hence optimized bracket is robust. 5. Experimental validation is done by strain gauge testing. Strain value measured at location of strain gauge is 153.2 microstrain. FIA value at same location is 180.7 microstrain. Hence, experimental and FIA results are same. 6. Performance of optimized bracket remains same as original bracket. Hence topology optimization is good method of optimization. 7. Topology optimization is furthermore effective if additive manufacturing technique is used for making of final part, as final part can be manufactured more similar to topology optimization output. So future scope is to study best manufacturing method that can be used for topology optimization part. Acknowledgement. The research support provided by the Singat Academy of Engineering is greatly appreciated. Also, special thanks to the Yoshwar Steels and NDT Testing Laboratory, PUN, for providing machining and testing support respectively.